Hello, my name is Ivan. I'm an undergraduate student of physics at Curtin University and a Pawsey summer intern. I've been working alongside the Institute of Theoretical Physics and Professor Igor Bray on a project titled GPU Acceleration for Antihydrogen Formation Calculations. Now, what even is antimatter? In physics, every type of particle has its associated antiparticle with virtually all of the same properties like mass and spin, but opposite electric charge. These, just like regular matter, can form their own atoms, with antihydrogen being the simplest one, consisting of an antiproton and an anti-electron. They can also form more exotic atoms, like positronium, a very short-lived but still bound state of a positron and an electron, which can be used in antimatter production. Now, why would we even want to research antimatter in the first place? Well, current theories suggest that the Big Bang should have created roughly equal amounts of matter and antimatter. Yet, almost everything we observe, from astronomical objects to regular things here on Earth, are made of ordinary matter, and we don't know why. Collaborations such as ALPHA, AEGIS, and GBAR over at CERN are searching for the source of this discrepancy with gravitational antimatter experiments, studying anti-atom behavior in freefall. However, to do so, they require a lot of antimatter, and this is a problem because it's not naturally found, as it's not long-lived, and it annihilates when it comes into contact with ordinary matter, so it needs to be produced at low energies to make experiments feasible. This is where our group's work comes in. With the conversion close coupling method, or CCC for short, we simulate the process of interest to provide cross-sectional data, which can be thought of as equivalent to probabilities of the reaction proceeding down a certain path. For the particular problem of antihydrogen formation calculation, these calculations are very lengthy and computationally demanding, so my work has been on optimizing and speeding up the code, in part using GPU acceleration. GPUs are very good at calculations which can be parallelized and are already employed in parts of the code to great success. Over the course of the project, profiling of the CPU version of the code revealed several redundancies, which found their origin in limited memory concerns from when the code was first written more than a decade ago, as well as some vectorization issues in the calculations themselves. Rewriting the code with those issues in mind, we were able to achieve almost an order of magnitude speedup for the more complex calculations. However, this left less time to spend on the GPU implementation, and no obvious part to GPU accelerate except for the entire calculation loop. Overall, mission failed successfully. A speedup has been achieved, which was our ultimate goal, just not using GPUs. Yet, it's still to be determined whether GPU implementation can be beneficial, and it also depends strongly on the machine being used. So far, testing has been done on the Topaz machine. However, with Cetonis coming out soon, with improved GPUs, different memory, and different memory transfer architecture, as well as many other factors, the viability of a GPU implementation may change. None of this would be possible without the Pawsey Supercomputing Center and this excellent internship program. The training was spectacular and tailored to the user's experience with using high-performance computing systems. The continued support from both the intern mentors and the Pawsey help desk ensured that everything progressed smoothly and no question was left unanswered. This was an incredible experience, and if you are looking to develop your skills and push your research forward, I highly recommend applying for the Pawsey internship.